So welcome everybody. So let's start with the invited speaker of first of one of this afternoon session. It's my pleasure to introduce all of you László Székelyhidi, graduated in 2000 from the University of Oxford and got his PhD in the Max Planck Institute in 2003 under the supervision of Stefan Müller. In 2011, he got a professorship of applied mathematics at the University of Leipzig. He has been awarded the Oberwolfach Prize in 2010, the Gottfried Wilhelm Leibniz Prize in 2018, and his main interests are, broadly speaking, partial differential equations and the calculus of variations. In the recent years, he has been working on mathematical hydrodynamics, specifically questions related to turbulence. So, and the talk of today will be, please, if you put it in, can you share the screen? Yeah. So the talk of today will be convex integration and synthetic turbulence. So László, please.
Thank you very much, Luis, for this very nice introduction, and thank you to the organizers for inviting me to this conference. And thank you all who are attending. I will talk about convex integration, which is a technique that has been developed quite a long time ago, but only recently adapted to fluid dynamics. And I will talk about synthetic turbulence, which is an expression that I believe was coined by Greg Eying, who has been, his work has been very inspiring to me. And it basically refers to turbulence which you produce by hand. Turbulent solutions which you produce by hand. So I will try to give a survey of recent results to this extent. Now to start the talk, so this will be an overview talk. I will keep it rather elementary. To start the scene, let me start by this quotation from Cyril Hinshelwood, who I believe was at Oxford University, who said that fluid dynamicists are divided into two classes: hydraulic engineers who observe what could not be explained, and mathematicians who explain things that cannot be observed. So he's referring to the great divide between what is being usually observed in fluid dynamics and what we can actually prove as mathematicians. And to be fair, he was referring to fluid dynamicists in the 19th century, but I think in some sense this remark even applies today, although we are trying to close this divide. To give an example of what he was referring to, this is the oldest problem in fluid dynamics, I guess, to calculate the drag force for a flow around the sphere. So you have a uniform flow with velocity u, and there's a sphere of radius L, and the question is just to calculate the force that this flow exerts on the sphere, or equivalently the force exerted by the sphere on the flow. And Newton dealt with this in his Principia, and he derived the following formula. So F is proportional to the density of the fluid times L squared times U squared. Then almost 100 years later, D'Alembert also studied this problem, and he derived the formula F is equal to 0. But he also was dealing with ideal fluids, which means fluids without any internal friction. This is something that Newton did not consider. And yet, 100 years later, Stokes also considered the same problem and derived the following formula, which looks, again, different. Although you can notice that if nu is equal to 0, the viscosity is equal to 0, it agrees with D'Alembert's formula. So who was correct? Because obviously, at least Newton's formula looks very different from D'Alembert and Stokes. And let me just say that Newton derived his formula based purely on, we would say today, dimensional analysis. He was making the assumption that F, so what can F depend on? What physical quantities? And then this is the only proportionality ratio that agrees with correct dimensions. Whereas D'Alembert and Stokes actually studied the Euler and Navier-Stokes equations, the stationary Euler and Navier-Stokes equations. So you see that somehow there is a big difference if you look at a physical approach using dimensions and a mathematical approach using the PDE. And it turns out that actually all of them were essentially correct. If you introduce the Reynolds number, the Reynolds number is this ratio, L times U divided by nu. It's a dimensionless quantity, which essentially refers to how turbulent the solution, the flow is. But typically, one expects, here I've written water and air, with, let's say, if there's a golf ball flying through water, or a car, flying through air, or a car at normal speeds. These are quite high Reynolds numbers. And essentially, small Reynolds number refers to laminar flow. And in this case, the formula of Stokes is more or less correct. But if the Reynolds number is large, it doesn't have to be too large. It's like the back of a car. Newton is almost correct. A second example is something, a very simple experiment that if you have children, you definitely tried, or you tried it as a child yourself. You take a straw, pointed upwards, and then a table tennis ball, and you blow the air in the straw and try to balance the ball above the straw. Okay, so it's actually not very difficult to do, which is why this is a nice trick. But mathematically, or let's say also physically, the interesting question is, why is it not so difficult to do? That must mean that this vertical position of the ball is stable. So here is another possible experiment that was drawn by my colleague in Leipzig, Jonas Hirsch. So here is the idealized situation. Here's the straw with some small diameter. There's air coming out at speed u, and there is this table tennis ball of radius L. And the question is, why is it stable? Now, this is something that in certain physics books, secondary school physics books, has an explanation, but that explanation is, I think, universally believed to be wrong. It refers to the Kelvin circulation law, which, the Bernoulli law, which doesn't apply in this situation. But more seriously, Landau, the famous physicist, did look at this problem in his famous, the book Landau and Lifshitz contains this calculation. Of course, you have to idealize, but the mathematical problem that he considered is that the cross-section of this straw is approaching zero. But of course, in order to have a constant force coming out, you have to have a Dirac delta right-hand side and it's again considering the stationary Navier-Stokes equations. And by assuming rotational symmetry, which is natural in this problem, Landau was able to derive the formula. But the formula gives a pressure distribution, which is something like this red curve. And you see that the pressure has a local maximum exactly at the axis of symmetry, which should mean that this is a highly unstable situation. So any small deviation of the ball will make it shoot to one side. So it doesn't agree with the observed stability. Okay, so a third example, which is more something that people have worked on in mathematics recently, is the what is called the law of finite energy dissipation in a turbulent flow. So let us take again the Navier-Stokes equations written here. The energy dissipation rate, which is the rate at which the kinetic energy is decreasing, which is denoted by this epsilon, is something you can calculate directly from the equation, and you get this formula, nu, which is the viscosity, times the integral of the gradient v squared. So it's coming from proportional to the viscosity and coming from internal shears in the fluid. But what has been observed for almost more than 100 years is that this dissipation rate, as the Reynolds number goes to infinity, that is, if you say you keep the dimensions of the experiment fixed, that means that the nu is going to 0, stays above a finite positive number. So here is a sort of rough picture of what a typical experiment would show. The Reynolds number increases. Here, what this CD is the drag coefficient in Newton's formula, but it's the same for the dissipation rate. Indeed, this observation that energy dissipation rate remains positive is in agreement with Newton's formula. So this is something that is difficult to see by just looking at the PD, because formally, if nu is going to 0, epsilon should go to 0. Of course, you might say, well, at the same time, gradient V has to go to infinity. And that's actually the point. Okay, so now I want to talk a bit about weak solutions, because they have different properties from strong solutions. And there's this nice quotation of John von Neumann that one has to talk not of one turbulent solution, but of many. There's probably no such thing as a most favored or most relevant turbulent solution. So my message from this sentence of Neumann is that uniqueness is a standard question that people look at, is maybe overrated, at least in the context of turbulence. There are other questions which might be more relevant. Now, I have a couple of historical slides just to emphasize that weak solutions are not a new artifact. Indeed, Euler, when he derived the Euler equations, it's, I would say, almost the first PDE ever written down, derived it essentially via, let's say, looking at little bits of fluid volume parcels, and indeed by using Gauss' law, the conservation of mass amounts to just saying that through any subdomain of the fluid, there is basically the total mass going out and coming in equals to 0. Total amount of fluid that goes out has to come in at a different point. And the same way, conservation of momentum amounts to the same total influx and outflux of momentum through any boundary has to add up to 0. Now, if you look at these red equations as the definition of a solution, there is no differentiability required. And so, in a sense, as soon as you can make sense of these boundary integrals, you can speak of a solution. And that's one way of starting to think about weak solutions. Going back even a bit further, weak solutions are probably as old as the theory of PDE. D'Alembert wrote down or derived the wave equation of motion for a vibrating string, and derived the general formula for it, which is given as a sum of two traveling waves. And you already noticed that in this formula, f and g does not have to be differentiable. But then he said, well, obviously, they have to be differentiable twice, because otherwise the equation doesn't make sense. And there was actually a rather interesting disagreement between D'Alembert and Euler. Euler was more of the opinion that you can admit weak solutions, let's say solutions where you have like sort of discontinuity in the derivative, like a triangle, because you can approximate that by smooth solutions, by smooth functions, and then the solutions remain close. This was, roughly speaking, his argument. And so somehow Euler's formulation was then proposed by Lagrange, which is similar to what Euler proposed for the Euler equations, and Leray proposed the same for the Navier-Stokes equations. This is what one could say a weak continuum formulation. Whereas there is another formulation which is by using Fourier transform, Fourier series for the heat equation, and Onsager looked at that formulation for the Euler equations. So this is a very old subject of weak solutions. Okay, on the other hand, if you look at weak solutions of the incompressible Euler equations, they are very badly behaved. And this was proved by Vladimir Scheffer in 1993 and later extended by Schnirelmann and joint work with Camillo Dell'Ellis. Basically, the statement is that there exist non-trivial weak solutions of the Euler equations with compact support in space-time. And the interesting part of that statement is the compact support in time, which means that the solution starts at 0, then it's non-zero, and then it's 0 again. So it contradicts all intuition of energy conservation, and the fluid starts to move by itself and then stops again. Okay, so this is clearly a non-physical solution. It's actually worse. One can prove that given any initial velocity field and final velocity field V1, there are infinitely many weak solutions of the Euler equations that start at V0 and end up at V1. So there is no really well-defined evolution if you look at the weak solutions of the Euler equations. You can get from any point to any other point in phase space. You might say that this is maybe something that's just wrong with the inviscid limit. Let's look at the viscous case, Navier-Stokes equations, but the same problem actually appears on the Navier-Stokes equations. And this was proved in a remarkable paper quite recently by Bookmaster and Vicol. Essentially the same statement. There are non-trivial weak solutions with compact support in time. Okay. So contradicts any form of physical intuition. And also in joint work with Maria Colombo, they proved also that the same type of statement, that from any V0 and to any V1, there are infinitely many weak solutions, going from V0 to V1. So again, somehow in the class of weak solutions, there is no evolution. Okay, so should we completely abandon the notion of weak solutions? Because so this is the state of the art somehow. But there is a close analogy to what is called hydrodynamic closure, and that's what I would like to explain. And here I just want to give a small quotation from Luc Tatar, whose work was very much inspiring for a lot of work that we did. The only thing about turbulence that everybody agrees upon is that it is created by oscillations in the velocity field. Now, the point is that you have to understand what type of oscillations and how those oscillations will change the behavior of the nonlinear term. And this is related to the classical closure problem. Now, in any physics book on turbulence, you will see the Reynolds decomposition, which is, let's say you have a turbulent velocity field, and we decompose it in a thought experiment into a kind of average or mean flow and a fluctuation. And this fluctuation could be, so the average, let's say, could be over a long time, which is what Reynolds did, or it could be over an ensemble or sort of with respect to a measure, which is what Kolmogorov introduced. Now, if you do that, the question is, what is the equation for V bar? And just formally, since you have this product, so the fluctuation appears in form of a Reynolds stress term. So this is the difference between averaging the product and taking the product of the average. And the big question is, can we find an equation for this extra term? Because otherwise, this is an underdetermined equation. There are just too many unknowns. And a priori, just by averaging, what we know is that this is a non-negative symmetric tensor. That's all. But we would like to have more information on it. Now, if instead, so let's say, so this is a way to see what is the effect of oscillations. It produces this extra term. Now, somehow, the what I've just said, the Reynolds averaging is this passage when you go from the Navier-Stokes equations in a sort of turbulence setting via averaging to something. But the closure model is something that you have to add, which is an additional modeling. On the other hand, you could just say, well, I can look at sequences of weak solutions of the Navier-Stokes equations. I look at weak convergence weak limit of a sequence of solutions. And in this way, I also converge to something very similar. This was something that was introduced by Di Perna-Maida in the case of the Euler equations, and also proposed by Peter Lachs in the context of dispersive equations. Now, on the other hand, you could also just look at the formal limit, look at weak solutions of the Euler equations. Of course, I just showed you that in some sense, this kind of relaxation is not the same because there is this extra term, but you might say, well, is there a relationship between these weak solutions and this relaxation? And that's what has been referred to recently as H principle. And the proof is by convex integration, which I will not be able to explain in detail in this talk. So, but just to give a flavor of what it gives, suppose you have a solution of this sort of unclosed system, which we'll let's call them sub-solutions. So now you have a V bar, P bar, and R bar. And the only thing we know about R bar is that it doesn't have to vanish. In fact, let's assume it's positive definite. Then the sort of energy, the total energy of the turbulent fluid, if you add back the fluctuation, should be something like this. So you have this, the kinetic energy of the mean flow and the kinetic energy of the fluctuation. And it turns out that any strictly subsolution of the Euler equations can be weakly approximated in a weak topology by continuous weak solutions of this particular class of Hölder class, 1/3 minus epsilon. And the 1/3 exponent has been something people were looking at because of, or shooting for, because of the Onsager conjecture. So this is something that was conjectured by Onsager, and because it agrees with the scaling laws that were derived by Kolmogorov. But for the purposes of my talk, I just want to focus on the fact that you can approximate strict subsolutions by weak solutions. So in some sense, the closure of the set of weak solutions in a weak topology is the full set of subsolutions. Okay, and that's the idea that I want to focus on for the rest of my talk. So, and I want to do that with 3 examples rather than some general framework. The first one is the Navier-Stokes equations. So let me just recall what Leray proved in 1934. He introduced the notion of weak solutions, which he called solution turbulent solutions, and he proved their existence. And his existence proof is based on the following 3 steps. The first step is to derive the following energy inequality, which does not just include the kinetic energy, which has to be less than the initial kinetic energy, but also so balanced by the cumulative dissipation over time. Now, that gives us, so if you have the set of solutions with this bound for some given initial data or given class of initial data, which is bounded in L2, that gives us this a priori bound. So the set of solutions is bounded uniformly in time with L2 in space and L2 in time with H1 in space. So that gives a certain bound on the set of possible solutions. And then what he had to cook up is some kind of regularization, some way of, say, finite dimensional, or which is now the Galerkin approximation, or what he did was regularize the equation itself. some sort of regularization. So in some sense, you return from the PDE setting to an ODE setting, let's say, cheating a bit, and then show that those solutions also satisfy the same inequality. And then you have to pass to the weak limit. So you have to show that as this epsilon parameter or the finite dimensional approximations goes to 0 or infinity, in the weak limit we have a solution. And that requires the sort of averaging or weak convergence that I referred to in the closure problem. But here there is something else, because we have this H1 bound, which H1 embeds compactly in L2, is something that was proved by Leray without any pre-knowledge, by an interesting proof, actually, very different from what people use now, that this is compact. Okay, now, let me return to the Bookmaster V-coil theorem, just to put this in perspective. They prove the non-uniqueness and wild behavior, referred to these theorems that I mentioned earlier, of weak solutions of the Navier-Stokes equations. Now, they are weak solutions in the sense of distributions, but they do not satisfy the energy inequality of Leray. Indeed, the solutions have finite kinetic energy. You can ensure even that the kinetic energy is bounded by the kinetic energy of the initial data, but they do not control the cumulative dissipation. The only control is in W11 in order to deal with the Laplacian term. And it's precisely this is the key point, because W11, the control we get from here, does not embed in L2. So we don't have any control of this quadratic term. To see that this is actually the main point, there have been a lot of other results of the same type. So, for instance, if you check in fractional Sobolev spaces, when you have embedding into L2, you require gamma equals 5/4. And indeed, Luo and Titi, soon after the Bookmaster V-coil paper, generalized their result to the case of hyperviscous Navier-Stokes, where you have the power of the Laplacian, which is exactly, so it has to be below the compactness range. And there's even more recent work of Cheskidov and Luo, where instead it's just controlling L1 in time. And again, you do not have an embedding into L2. So the main difference, and somehow what is underlying these two results, is that in the Ray's case, he identified a notion of solution which is stable under weak closure. So you take the set of possible solutions of the equation, you close that weakly. That means you look at possible fast frequency, large frequency oscillations, and the equation remains the same. Whereas in this case, it does not. Another variation of the same theme is if you look at the P Laplacian, so these are called non-Newtonian fluids, as the dissipative term, then you can even look at the Ray solutions. So ones which satisfy the energy inequality of Leray. But now you have the P's power of the gradient of V in the inequality. And again, the first thing you should ask yourself, do you have a compact embedding into L2? And this happens if and only if P is bigger than 6/5. And indeed, there are these two results. One has the existence of Leray-Hopf solutions via the compactness argument. Essentially, it's the argument of Leray. If P is bigger than 6/5, although now we don't know much more about that, but the same way we don't know much about Leray-Hopf weak solutions of the Navier-Stokes equations. And but if P is less than 6/5, we have the same kind of wide behavior, non-uniqueness, and the same techniques that Bookmaster V-coil introduced. Okay, a second example is the 2D vortex sheet problem. So here, what So if you remember this one picture where you have the uniform flow and the ball of radius L and some kind of turbulence or wake, turbulent wake behind the ball, one of the interesting questions is to understand the evolution of this, let's say, so here I cannot draw it. So the transition between laminar and the turbulent region. And one way to do that is, well, to simplify the problem, you look at a plane orthogonal to the flow, called the Treft plane in the physics literature, and just study somehow a simplified evolution of this boundary on that plane. And this leads to the vortex sheet formulation in 2D. So you have here the velocity field, which has a certain vorticity, is supposed to be a measure concentrated on a curve. Okay, measure concentrated on this curve. And once you know what is the vorticity, you can calculate the velocity back from, so here gamma would be the strength of the vorticity, and z is the curve where it's concentrated. So this is the Biot-Savart law. Now this also has a long history. The law proved in a landmark paper in 1991 the existence of weak solutions for positive vorticity density. I'm simplifying things a little bit just for the purposes of the talk. Essentially, Lerais' proof is based on Delors' proof is based on Lerais' strategy in the following sense. In the first step, you identify what is formally conserved by the evolution, and in the 2D case, this is the vorticity. In fact, any LP norm, because vorticity is just transported, but in particular, the total mass of vorticity is conserved, and that allowed Delors to pass to the weak limit. Although here it's not a compact embedding, it was a much more complicated proof relying on compensated compactness, which I will mention briefly later in a slightly different context. So Delors realized that even though we don't know if V squared is converging, like in Lerais' case, but the key point is that if you remove the trace from this V tensor V, you can put it on the pressure, and the traceless part consists of these two components. Traceless part of this 2x2 matrix, and these two components are weakly continuous. Okay, so it's again a strategy of existence by compactness. And as usual, the problem with these proofs is that we have very little information coming out of the existence proof on how these solutions look like or what further properties they might have. Now here, in the case of the vortex sheet problem, there is an earlier approach, much earlier, originating from the 19th century, which is based on the fact that if we assume, this is an assumption, which is not necessarily satisfied, that the vorticity remains a measure on a well-defined curve. So there is a ZT and the vorticity strength gamma t, such that omega is this measure. Then, of course, again, you can calculate what is the velocity, and from this, going back, you can derive an evolution equation for the curve. That's the Birkhoff-Roth equation. Unfortunately, this equation is ill-posed for everything except analytic data. So you have a Cauchy-Kovalevskaya type theorem, but basically nothing else. And the reason for that is that it's you have these very bad instabilities, which are somehow physical. They appear as what is known as Kelvin-Helmholtz instabilities. So there's a roll-up of the initial surface, which starts to lose all regularity you might need for the equation. On the other hand, so this doesn't give you an existence like this strategy doesn't give you an existence like Delors' strategy. On the other hand, it gives you geometric information on what is going on. So in a recent work with Fran Mengual from Madrid, we were able to somehow combine the two approaches with convex integration. So we were able to prove the existence and at the same time non-uniqueness of weak solutions to the vortex sheet initial data with certain kind of initial data. It variance with the loss result with only the sign condition on the vorticity. And the strategy is basically the following. You start with this vorticity on the curve, but we don't make the ansatz like Birkhoff-Roth. We just make the following ansatz that starting from that initial curve, there is going to be a slightly deformed curve, z of t, around which there is a turbulent zone. So we don't try to resolve these little roll-ups, these spirals. We just say that there is a turbulent zone in which the solution is just a weak solution, but it's bounded by, it's growing linearly in time, and it's bounded by translates of the original curve. So, and outside, it has to be a smooth solution. It's analytic, actually. Okay, so how to construct such solutions? Well, the idea is just to look at the subsolution equation, which I had earlier. So this equation we get from the closure ansatz. So we have this additional R, and then making this, so you have this these boundary curves, gamma plus and gamma minus, which are just translates of the original curve, which is also evolving in time. The equations reduce to a boundary value problem for this tensor. So it's divergence of R is equal to 0, and the normal components have to equal something on the two curves, where this something is given by the time derivative of the mid curve and the normal component of the velocity. So observe, if you are familiar with the Birkhoff-Roth equation, if R is equal to 0 and gamma plus is equal to gamma minus, so then this is 0, this expression, and this is precisely the standard way to derive the Birkhoff-Roth. Okay, so this is a sort of relaxation of it. And so here I've written it again, and basically the only additional, you see, this is still underdetermined because we have a tensor here and just one equation. But the additional condition is that the energy should not increase, this admissibility condition. And so we have to somehow control the total energy. And it turns out that the energy dissipation rate can be calculated by making this ansatz. And it, of course, it depends on how quickly, so this C was the speed at which these curves were, the turbulence zone was growing. And so it depends on C and the vorticity strength. And so let me just try to give a small video to explain this. Let me see if I can do it very quickly. Yes. So I hope you can see this. What Fran calculated here is I hope you can see it well. The light blue curve is essentially the standard regularization of Birkhoff-Roth. You see this roll up happening, and the two dark blue curves are the curves that we calculate from this ansatz. So how fast, I mean, first of all, they are deforming, and they're also, there's an opening up rate. Okay. And the second picture is showing that you don't have to have constant sign. So at the red points, the vorticity strength is 0. And so you see it doesn't affect our technique. Okay, so this technique doesn't give you precisely how the roll up happens, but it gives you an idea of the mean dynamics. Okay, let's see. Almost over time. So very briefly, the third example. This is magnetohydrodynamics. So here I have the Euler equations, which are coupled with a magnetic field, which is supposed to satisfy the Maxwell equations. Now, this is a very rich system that has been very much studied. There are several conserved quantities, the total energy, which we have like in Euler. There's a cross-helicity term, which is essentially pretty similar, and something else, which is a Maxwell invariant, the magnetic helicity. And this arises from the inverse curl of A, which is the vector potential of the divergence free vector field B. And of course, it has been studied under what conditions these conserved quantities are conserved. Actually, for weak solutions, I just refer to the paper of Kaflish, Clapper, and Steele here. Now, let me just say a few, very quickly, why is this interesting physically? Well, so of course, in reality, you have some viscosity, and there's also a resistive term in the Maxwell equations. These are both dissipative terms. But what is observed, let's say, in the solar corona and turbulent plasmas, is that there are two time scales for the dissipation in this system. On a short time scale, the kinetic energy dissipates, so that's due to this term coupled with this term, the same way as we have the law of finite energy dissipation in hydrodynamic turbulence. If that happens, V is going to get very small. If V is very small, not much is expected of this term. So somehow the magnetic field does not dissipate as fast. Here you only have, if you ignore this term, you only have the heat equation. On the other hand, it's still there somehow. So what people observe is that on this longer time scale, the magnetic field relaxes to a minimum, which is not zero, but the minimum subject to given magnetic helicity. Okay, so this is known as the Taylor-Voltaire relaxation theory. And the usual explanation for this is by somehow magnetic reconnection. So if you didn't have this term, this would not be possible. And this is somehow why NASA is making this experiment to study this magnetic reconnection. But there is a mathematical explanation, which is due to the Diffie-Hellman lemma of Tartar and Murat. So basically, the Maxwell system is this one. There's the electric field, and in the case of MHD, it's perpendicular to B. But if you apply the Diffie-Hellman lemma to this system, you see that E dot B, precisely this quantity, is a compensated compactness quantity. It's weakly continuous. And this appears precisely in the magnetic helicity conservation. So indeed, it was only recently proved that if you look at nu and eta going to zero in the indissipate resistive limit, magnetic helicity does remain a conserved quantity in the 3D MHD. And this is expected. So conservation of magnetic helicity. At the same time, like in hydrodynamic turbulence, we expect anomalous dissipation of energy and cross helicity. And it was proved recently by Beaky, Bookmaster, and Bicol that you have existence and non-uniqueness of weak solutions which do not conserve anything. They do not conserve energy, cross helicity, but also not the magnetic helicity. And these are, let's say, very weak solutions which are in the energy space and some very tiny amount of Sobolev regularity. And what we were able to do is to prove the existence of bounded weak solutions which do not conserve energy and cross helicity, but the magnetic helicity has to be conserved. Now, it looks like the statements are very similar, but there is a big difference. If you have bounded weak solutions, magnetic helicity has to be conserved. And the technique of Bookmaster, Bicol, and Beaky cannot be used for this. And just the last slide, sorry, Luis, to go over time. The approach to do this is to look at the correct closure of the system. And so this is like this relaxation or closure problem, or the definition of the correct subsolution. Like in the Euler case, or Navier-Stokes to Euler, there is a Reynolds stress term in the momentum equation. But in the Maxwell term, we have to basically realize, essentially based on the Tartar-Murat Diffie-Hellman lemma, that the electric field is still constrained to be perpendicular to B. And once you realize this, and then use some tricks and technical details, you can construct such weak solutions. So I just wanted to emphasize again the importance of understanding the weak closure of the system of equations under consideration. Okay, thank you for your attention.